Happy St. John the Baptist name day to everybody. Our speaker today is Elena Caceres.
Thank you for the introductions. Thank you for being here, and thank you to organizers for inviting me. Yes, there are fireworks tonight, I've been told, because it's some John the Baptist. So, okay. So today I'm going to talk about different things related to sparse SYK. This is work done in these papers with my students, Anderson Misobuchi, Rafael Pimentel, and Amir Ras. And then maybe I might show you a little bit of something in progress. Cool. So first, this is more or less the plan of the talk. I will introduce the sparse SYK, just to remind you what is it about. Then I'll do a little detour into hypergraphs because it's a useful tool to study this type of models. And then essentially, then I will just show you some results about two coupled sparse SYK, traversable wormholes, revivals, and then the spectral form factor. Okay, and then I will talk about mention some future directions. Okay, so just to be on the same page, the all-to-all SYK, so I will refer it to all-to-all or dense SYK, is this quantum mechanical system of n major n fermions with all-to-all random interactions. So you have your, is it pointing here? Your couplings drawn from some random Gaussian distribution with zero mean and variance given by this expression. It's analytically solvable at large n. It has an emergent conformal symmetry at low energies. It's maximally chaotic. And because of all these features, it is probably our best toy model of holography. And it has been studied a lot. The drawback is that even though we do have like exact results at large n, if we want to study large but finite n, if we want to do numerical simulations, then this is computationally very expensive because the number of terms go like n to the q. So we're talking about millions of terms. The state of the art for the SYK is around n equals 52. So we're talking about millions of terms. So if we want to study finite n in the idea of like to see gravity when the system starts to become having a gravitational dual, how these features appear as we increase n, it's very hard to do numerical simulations for some things in the SYK. So a natural question to ask is if there's an SYK modification that will retain all the good physical properties, but it will be more computationally efficient. And the answer is yes, and that's the sparse SYK. So the sparse SYK was put forward, by Xu, Saskin, Su, and Swingle a couple of years ago. And it consists really in making the system sparse, so you remove some of the terms to reduce the number of terms in the Hamiltonian, but keeping the features the physics that you want, right? Like the chaotic behavior, for example. Now, there are issues about, there are questions about how do you introduce the sparseness, and a very important one is how much sparseness can you have? How sparse can your Hamiltonian be, your system be? So let's take a look at two ways of introducing sparseness. The first one is by random pruning. So random pruning, you have this extra parameter here, this little x's that now can be 0 or 1 with certain probability. So of course, if your probability p is 1/2 or 1/4, you have not done much. But what we're interested in is the case when this probability is really small, right? And so then you reduce the number of terms considerably. Now, random pruning is very intuitive to understand because you're just removing some of the couplings, but it has some issues that you are not guaranteed that the whole thing is going to be connected anymore. You can have some patches of disconnected groups. So the other way, oh no, not yet. Let's say that we want, for example, the computational cost, we can reduce that with the sparseness. Let's say that we want, instead of having n to the q terms, we want kn where k is of order 1. So we want it to be linear in n. Well, we just have to choose a probability like so, like n choose q times p equals to kn. So that's a very small probability for large n. But with this, we guarantee that then we have a linear in n terms in the Hamiltonian. So instead, like for n equals 52 and k equals 4, instead of having millions of terms, now we have order of hundreds of terms. Okay, now we can do more numerics. We can study higher n, and we can study higher q, which in the SYK literature, you probably will have noticed whenever there's numerics, it's all constrained to q equals 4 because it's very hard to do numerics for q equals 8 or larger. Okay, so this, as I said, this model was put forward by Xu, Susskind, and Swingle a couple of years ago, where they study also, they have a path integral formulation for it. And they conjecture that they saw that there's they conjecture that there's the same pattern of symmetry breaking as in the all-to-all SYK, and that therefore this sparse model is also going to have a gravity dual. However, the issue of exactly what the gravity dual is not so clear as in the case of the SYK, because they can see that you have the Schwarzian mode, but you have the Schwarzian mode plus other stuff. So, okay, but it's a very interesting model to study. There are many things to be done, and something where we can play a lot and do a lot of numerical concrete calculations. So one of the first things that we should answer is, given this sparse model, how sparse can it be in order to still keep the good physics that we want? And then can we see something new by, I'm saying that, oh, we can do all these numerical simulations and all that. And so what is this good for? I mean, what do I gain from better numerics? So that's essentially the couple of things that I'm trying to answer this talk. But first, we have to talk a little bit about hypergraphs. Okay, because I told you that there are two ways of introducing the sparseness. One was random pruning that I just said. The other one is to realize the model over a hypergraph. And that way of introducing the sparseness is much more like control. It's going to be much more useful for us. So hypergraphs. Okay, hypergraph is just a generalization of a graph where the hyperedges can connect more than two vertices. So instead of having two vertices, this is a graph. It's defined by these two sets, V and E. V is a finite set whose elements are called vertices. And E is a set of pairs of vertices. So E here, the thing is that the cardinality of this E is 2. They are pairs of vertices. That is a graph. A hypergraph is, again, two sets, a set of vertices and a set of edges. But the E is a non-empty subset of B. So you don't have to have only two vertices in a hyperedge. You can have any number of vertices in a hyperedge. So that's the definition, essentially, of a hypergraph. So it's really set theory. And the literature in graph theory has been, there's a ton of results. And when I started looking into this, it came to kind of a surprise to me that hypergraphs, though, even though they are like used right now in many things, from recommendations that you get in the internet to how fake news propagate, to neuroscience, they are used everywhere. The mathematical results, I mean, they do not completely like extrapolate just from graphs to hypergraphs, and there's a lot of new results in hypergraphs. So some things that are very well known for graph theory, they are not as established in hypergraphs, and you will see that I will mention some results that are from 2019 from mathematical results. Okay, so from all the possible hypergraphs, we are going to be interested in hypergraphs that are regular and uniform. Okay, what does that mean? So if it's uniform, means that every hyperedge contains S vertices, if it's S uniform, okay? And that's fine. We have our Hamiltonian, that each term in the Hamiltonian has a second pair of Majoranas, so it's going to be uniform. Okay, if it's regular, it means that all the vertices are contained in R hyperedges, in the same number of hyperedges. Okay. So this is something we're going to impose to our hypergraphs. There are some results for random, regular, uniform hypergraphs that we're going to use. So we're going to be looking at this type of regular and uniform hypergraphs. Okay. Yep. So the sparse SYK, we're going to define it over a KQ. Remember, Q is the uniformity, and KQ is in order to have this linear in n number of terms over KQQ hypergraphs. The Majorana fermions are identified with vertices, and each interaction term corresponds to a hyperedge containing Q vertices, so it's Q uniform. Right? KQ regular, every vertex is contained in exactly KQ hyperedges. Yes?
Can you just clarify this notation, KQ comma Q? KQ is the regularity parameter and Q the uniform?
Yes, it's this RS regular, S uniform. So this is the standard notation.
So this is to say that every Majorana fermion is, okay, all of the couplings are with Q minus one other fermions. And what is the first one telling me?
This one is saying the S uniform is telling me that every term in the Hamiltonian has Q Majoranas, right?
Right, and how should I interpret the first?
Yeah, the first one,
physically?
we are imposing that, and you will see in a second that it's what I want. Intuitively, you can say I want it to be very regular. It will guarantee that the whole thing is connected, and it will make calculations much easier. So this is an imposition. This is not something that you can just see from the Hamiltonian. Okay. Okay, Q uniform indicates the Hamiltonian contains Q-body interaction. So here, K now is I'm going to quantify the degree of sparsity in the Hamiltonian. So K is the P, the probability divided by N times N choose Q. Okay. So with this definition of K, and given that it's a KQQ hypergraph, then I have Kn terms. Okay. And so when we will use some results for random, regular, and uniform hypergraphs. Okay, good. So what do we want to know about these hypergraphs? We want sparse hypergraphs that are highly connected. These ones are called expanders. Okay. So essentially, we want to somehow find out how much sparsity can we have, but still keeping the hypergraph to be an expander. There are several measures of connectivity. like the one that I'm going to show is called, one is called algebraic hypergraph entropy. The other one is called vertex expansion. All of these, these two ones really are controlled by the spectral gap of a hypergraph. So you could say the spectral gap is also a measure of connectivity, but somehow it's a thing on its own, but it controls the other, the vertex expansion, the hypergraph entropy. Okay, so spectral gap, what is the spectral gap? So in a hypergraph, everything has to do with the adjacency matrix. The adjacency matrix is the one that gives you the information about the structure of the hypergraph. The adjacency matrix is defined this way. So each element A, I, J, where I is different than J, gives me the number of hyperedges containing vertices I and J, and 0 they are equal. That's the adjacency matrix. Okay, that's a matrix. It has certain eigenvalues. The largest eigenvalue can usually be determined, so you can know the largest eigenvalue of your adjacency matrix. So it's really the second largest eigenvalue that contains the information about the gap. And that's the one that we would call the spectral gap. Okay. What is in this plot? In this plot is lambda divided by lambda max. And this is K. And this you see for, remember, I'm trying to see which K is good, how much sparseness can I have? And these are different ends. And this is for the dashed line is for n equal 24 here and n equal 40, but for the SYK. So I can calculate, I can realize the SYK also as a hypergraph, and I can calculate its adjacency matrix, and the adjacency matrix will be something very simple. I think every element is n-2, choose q minus 2, something like that. And so I can calculate the spectral gap. And so this is the value for the SYK. So the more these other guys approach the value of the SYK, you would say it is better, more similar to the structure of the SYK hypergraph. So that's just the spectral gap. What about these other things, which are somehow more refined measures of connectivity? Somehow the spectral gap is just the one that is going to enter in all these things, but the algebraic hypergraph entropy is defined like this. So you have a hypergraph and you have the adjacency matrix. Then you can define this matrix, this diagonal, where all the entrances are just the sums of the AJs. And mathematicians have studied, and they say that this operator normalized like this, 1 divided by trace of d minus AH, with eigenvalues nu I, then I can calculate the algebraic hypergraph entropy just like nu I log nu I. And that is a measure of connectivity of the hypergraph. As you can see, it all depends on the adjacency matrix also, and therefore in the spectral gap. And here we can see the results. So again, the SYK you can calculate exactly because the SYK adjacency matrix is just all constants, I mean, very simple. And these are different ends, and 24 here, but different Qs, Q equals 4, Q equals 8, and here different Ks. And well, you start noticing that it's kind of intuitive, but for Q equals 8, so the red one here approaches much faster the SYK value than the Q equals 4, right? Same thing here. The Q equals 8 is the orange one. It approaches much faster the value of the, yes?
So for the previous measure, the lambda over lambda max,
Yes.
it didn't seem to be converging as quickly as this one.
Indeed. It does not converge as quickly. This one does not converge as quickly. That's why I'm saying, I mean, I'm just showing you different measures of connectivity. Which one, my philosophy when looking at this was, I want to see how much I can get out of Hypergraph, right? So this one does not converge as quickly, but you can still see this feature that is going to be kind of one of the things that I'm going to use, that the Q equals 8 is always converges faster than the other ones, right? And the Q equals 4. So essentially, the optimal K or the minimum K depends on Q, right? For larger Q, I can get away with a smaller K. And that's going to be the lesson of these measures. So yeah, I mean, what I'm just showing you different measures, and yeah, so this was the algebraic hypergraph entropy. And then we have vertex expansion. So this one is a little, so if we consider a subset of the set of vertices, we can define its neighborhood, right? By J that belongs to S, and essentially who is connected the neighborhood to the neighborhood of this subset of V, right? And this is a recent result, well, recent 2019, but relatively recent, right? Result by Dmitry and Shu, it's a mathematical result, but they prove that there's a lower bound on vertex expansion this is 4 random, regular, uniform hypergraphs. And so this is the neighborhood. So essentially, what this ratio is the size of the neighborhood divided by the size, the cardinality of the subset, right? And these guys prove that it's bounded, like so. Yes.
Is there some assumption about the size of the set?
Yes, the size is less than half of the whole set. Yes, indeed. Yes.
I'm having trouble understanding where the randomness comes in, because this is an exact statement.
Where the randomness what?
Well, in what sense does this hold for random graphs? It seems to depend on the spectral gap, I think that's what the lambda is, and the uniform and regularity parameters.
Well, from the result, I cannot see it, but it's from the proof of what these guys did. So I will have to refer you to the paper, I guess, because I don't remember off the top of my head how the proof went. But it's for random regular uniform hypergraph.
So is the point that, I mean, one can design hypergraphs that violate this, but a typical hypergraph obeys this? Is that the sense here?
That will violate this particular one?
Yeah.
Or in general, what do you mean?
But you said this bound holds for random graphs, hypergraphs?
Yes.
So is the point that one could design a hypergraph that violates this, but a typical
yeah, but if it's completely random, yeah.
a typical hypergraph obeys this?
Yeah, I think so. Yeah, I think that's it. That's the point. Yeah. Well, okay, so this is the how this compares to, again, the SYK value. This one converges also. Again, Q equals 8 converges much, much faster to the SYK than Q equals 4. So these are just measures of, so what is the lesson from here?
Wait, can I ask you a question about that? So
yeah.
Are we picking a random S, or this is for any S? Because it depends on S, right?
What is, no, it's, remember is,
I mean, big S, the set.
Yes, that's what Patrick asked. So the only constraint of the set is that the subset is that it's less than half the size of the whole set.
Right, but in these graphs, did you just pick a random S, or it's an expectation value averaged over S, or?
For the subset, you mean?
Yeah.
No, in this, let me see, no. Yeah, I'm finding the lower bound. So I'm just plotting the lower bound.
Oh, you're plotting the right-hand side of that?
Yeah, I think so, yeah.
Oh, I see. Okay.
Okay. Now, this whole thing is just to show that Q equals 4, K equals 4 seems to be good, and Q equals 8, K equals 2 seems to be good. So for larger Q, I can get away with a smaller K. But also, I mean, so I'm not going to move away now from hypergraphs, but this opened the whole, for me, the whole new field of trying to learn about hypergraphs, because it's really neat. And there are a lot more of things to be done. Like there is something called covering times, which essentially is, imagine you have a message you enter in some vertex, and then you random walk through the hypergraph. And there are different covering times. There's vertex covering time, edge covering time, information covering time, which all depends on how do you walk, and is as you walk and you see the other edges, are you informed of that or not? So different definitions of covering times. They all scale like n log n. And it's very suggestive that this type of measure will have some kind of application for our Hamiltonians too. But anyway, that is one thing. Then there's the issue of hypergraphs can be directed or can have colors. And you can think that maybe if I were to consider some conserved charges, I will need some of those, like some colors or something. I don't know. There's just a lot to be done. Okay, so from hypergraphs, what we kind of, the takeaway was that it's really nice. It gives us information about the structure of the Hamiltonian, how expanded it is. And then the question is, of course, this does not tell me about the dynamics of the system. But remember that one of the questions at the beginning was how much sparseness can I have? And I think we can use hypergraphs to have an idea of that. Okay, so I'm going to move on to traversable wormholes. And this is essentially based on what Maldacena and Chi did for the SYK, the all-to-all SYK. And you have two SYKs, and you couple them with this interaction, left and right. This is in gravity, this was first proposed by Gao, Jeffries, and Wald, this type of, Gao, Jeffries, and Wald, by this type of, that you turn on some interaction that couples the boundaries, and then you can see how the structure is deformed and the wormhole becomes traversable. And Maldacena and Chi did it for an ADS2 geometry using JT gravity. And well, the idea is that the same physics, we should be able to derive it from just coupling two quantum systems, just from quantum mechanics. This is nothing to do with gravity, it's just quantum mechanics. So, so I would have a left Hamiltonian and a right Hamiltonian. I'm going to couple them with this interaction to couple the sparse SYKs. Okay. The properties that Maldacena and Chi studied of the system is that the ground state is approximately a thermofield double. And very importantly, the energy gap scaling goes like this, like mu to the 1 to the 2 minus 2q at weak coupling, and goes linearly with the coupling at strong coupling. And this is the phase where it's a traversable wormhole. So this was derived from a gravitational analysis. And the question is, this is the energy gap, right? So I can compute that in my quantum mechanical system. And I can see if it scales like this, right? And it's a non-trivial scaling, because for Q equals 8, I think it's 7/4 or something like that. Something, it's not a pretty number. So that's what we did. And here it is. So this is Q equals 8, K equals 2. So this is the energy gap. These are the different ends. The dotted line is the mu, the linear scaling, and the dashed line is the 7/447 scaling that is the non-trivial thing that we're supposed to get if we have a traversable wormhole. So this plot is one of the ones that I like the most, because you can see that we indeed have precisely for a small range of couplings, it follows precisely this scaling, and then as the coupling grows, it just goes completely to the linear scaling. What goes on here, I do not know. Probably, I don't know, 1/n effects become important. I don't know. The numerics, this is what it keeps, but it does reproduce the scaling of a traversable wormhole. So that's one thing that we did. I don't think I have it here, but we did the same thing for Q equals 4, and it didn't work as well. As I was telling you before, Q equals 8 always seemed to converge faster to the SYK, right? Q equals 4, even though we went to higher K, we were not able to see this clearly. So, okay. So Q equals 8 matches the scaling expected from gravity for large N and appropriate range of couplings, and finite N dominates at very small couplings. I mean, it could be one of the reasons why that doesn't work at very small couplings. Okay, now revival dynamics. So what is this revival dynamics? This is something characteristic of chaotic system. So we start with a ground state of the two coupled SYK, and we create a Majorana excitation in the right, and the excitation gets scrambled. And because this thing is chaotic, the excitation reassembles itself and becomes localized in the left of the system. And then this again becomes the starting point, and you repeat back and forth. And this process is repeated. This is called revival oscillations. It was studied by these guys for the SYK, for the dense SYK. And the gravity picture is that the perturbation is traveling through the wormhole. And there is a very precise, so I'm going to show you some plots about how this, we can calculate like a transition amplitude and how this oscillates. But the frequency of the oscillations is also important, because the frequency of the oscillations is related to that plot of the energy gap that I show you. So from the frequency of the oscillations, you should be able to recover the same scaling of the energy gap that I show you, and it does indeed happen. Okay, so we find a transmission amplitude like so. So we have our green function, left and right, left and right, left, left, right, right, at time 0 times 0, and t left, right squared, it will give me the probability of recovering the chi left at some time t after having inserted it in the right-hand side at time 0. Okay. So this is the result for the SYK, for the dense SYK. And you can see, okay, so what are these? The orange is left, left, and the other one is left, right. So you can see that as one increases, the other one is in its bottom photon point, and then this whole thing repeats, right? So it traverses, and then it goes back, and then it goes back, it goes back, and then there's an envelope. Like as time goes by, there's an envelope like a power law that reduces and reduces. And these are the different effects for different mu's, different values of the coupling, 0.01, 0.01, 0.1. So you start increasing the coupling and the thing starts like misbehaving, disappearing, as you would expect, because as we saw, it's for small couplings that you expect to be traversable wormhole, and as large couplings, you don't expect that amount. So that was the result of these guys. So then the question is, can the sparse SYK do the same thing? And this is it again with Q equals 8. With Q equals 4, everything is a little bit murkier and the numerics are not so clean. Again, we see these oscillations. These are different temperatures, beta 0, 25, 50, 100, and the left, and the right. So we do these oscillations, and we can calculate the frequency of the oscillations. So yes, it does. The envelope seems to be like, it is decreasing faster somehow, but yeah, but the oscillations are there. So that's the traversable wormhole.
Wait,
so
can you go back to the, actually the one before? I didn't understand what TSYK is.
TSYK is the uncoupled one. If you didn't have them coupled, so it just goes to 0. It's just 0 essentially.
I see.
And the other ones are when you have the coupling and the effect of the coupling. Okay. So the summary so far, the hypergraphs are a useful mathematical framework that provides information, connectivity about the sparse model. Sparse SYK is computationally tractable. And with emergent gravitational behavior and two couples SYK, this private traversable wormhole. The tools I have to acknowledge, for everything that is evolving in time, we use this package called Dynamite, developed by some people at Stanford. And then for all the computations, we use the Texas Advanced Computing Center. So, okay. Now, moving on to chaos and the spectral form factor. So far, I have shown you that we can reproduce essentially the SYK physics with the sparse SYK with some appropriate Q and K. So then the other question is, can we see something that we have not seen in the SYK because of numerical limitations? And that's when the spectral form factor comes in. So quantum chaos, our standard one of way of diagnosing quantum chaos is the autocs, out of time, or the correlators. That, if I have time, I will show you something at the end. But the other one is random matrix theory, right? So random matrix theory provides an alternative diagnostic of quantum chaos, and it's encoded. If a system is chaotic, then its properties are encoded in the statistical properties of the spectrum. Okay. That's RMT. And a quantity sensitive to energy level statistics is the spectral form factor. So this is just this kind of analytically continued partition function. And this is the spectral form factor. And it has a disconnected piece, where this is just Z times Z. And it has a connected piece, which is the total thing minus the disconnected, right? Okay, so it has disconnected and this disconnected piece. And this has been this is the famous result by Kotler et al. From several years ago now, that at early times, So remember, I'm doing everything that I'm doing is quantum mechanics. I'm not doing anything gravitational now. That's like what I want to do next. But the result is that this is the spectral form factor for the SYK. It has the famous slope, the dip, the ramp, and the plateau, right? And the idea is that gravitationally, this slope part is telling us, or represents two disconnected geometries. And then all this other part represents connected geometries, wormholes, a new saddle in the path integral. Okay. And so this was a big deal. So it's disconnected here and it's connected here, and these are the wormholes here, and these are the two disconnected geometries. Okay, so at early times it's dominated by the disconnected, and at late times it's dominated by random matrix theory, the connected thing. Okay, but one can ask, how does the connected piece go at early times? Because here we're just looking at the connected piece at late times, but one could ask, how does the connected piece go at early times? And this was analyzed by Vertex et al. In 2020. And they found that the connected contributions can dominate at early times. It's essentially an expansion in higher moments of the distribution. And the connected piece at early times goes like this. And the critical parameter here, the important parameter here is this epsilon, which is the parameter that they do their function, is like n choose q to the -1. So essentially n to the -q. So they did all this analysis, and they concluded that it is possible that it can dominate at early times. However, we would need very high n in order to see that. Because what happens is that for lower ends, you calculate let's call critical time, the time where the early time, where the connected piece starts dominating. So for n equals 30, 40, which is the standard for the spectral form factor, that critical time and the dip time coincide, essentially. So you cannot distinguish them. You cannot tell them apart. You will need to go to much higher n in order to distinguish these two times. So, but nobody can do n equals 60 for the spectral form factor. So what we said is, well, let's try to see if the sparse SYK can help here. And we found that the same analysis as Vertex et al. Goes through. Now our couplings are non-Gaussian couplings because we have deleted some. But there's a result by these mathematicians, Feng, Tian, and Wei, that essentially tells us it can only depend on the fourth moment. And if we calculate the fourth moment, well, it gives something like this, 3/p in the fourth moment. Okay, so now the epsilon, instead of being n choose q to the -1, so n to the minus q, is n choose q to the -1, but times 3 divided by p. But p is very, very small, right? So overall, this is going to be, if I rewrite p in terms of k and n, blah, 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 this contribution is of order 1/n instead of being 1/n to the q. So it's much easier to see it now. And this is what we get. So the red thing is the disconnected. So the disconnected starts here, as we would expect. But the blue one is the connected. The blue one is the connected. So at some critical point here, the blue one starts dominating. And it's really the blue one that the connected one that dominates over the disconnected one at early times. This is for n equals 30, k equals 4, q equals 4, and here is the dependence of this critical time as you vary k for different temperatures. And what I was saying is that in the SYK, because you had this 1 over n to the q, this time coincided almost with the dip time, so you couldn't tell them apart. But in the sparse SYK, we need less n to, and we can look at more things. So okay, so that's what we see. What does it mean from the gravity side? I don't know, but this is, as I said, this is just what we see from quantum mechanical model. Yeah, I have heard many potential explanations, but okay. But it's probably not this subtle. So this was the subtle of the wormholes. It's probably not that. It's probably fluctuations around something else. I don't know.
Can I ask one thing? Hi.
Yes.
Yeah, it seems like this connected piece, this randomness is much smaller than connected piece, and even into the plateau region. Is that because of sparsity, or am I confused with something?
The what? Sorry.
Like in a plateau region, it looks like this standard.
Are you talking about the
randomness
oscillations?
is smaller than.
I think
standard
that's
deviation seems to be
just
smaller.
that the line is a lot less jagged. The blue line.
The oscillation, yeah. So typically the sparse SYK is not self-averaging. So even for the sparse SYK, for the all-to-all SYK here, there are fluctuations that you need to average in order to get like a smoother line. For the sparse SYK, the fluctuations are larger. We would need to, I don't remember how many disorder realizations we had here, but we might need to do more averaging. I don't know. It's the main point is here, yes, which is not affected by the fluctuations.
Oh, yeah. Okay, I think, yeah, connected piece not being affected by a fluctuation, I totally can understand, but it's, anyway, okay, I'll think about it.
Okay, what was this? This is the total one. This is the total one. This is so the total, you can almost not see it. It's a blue line that is under the green one, so the disconnected in the beginning, and then the connected. So the blue line, if you can see here, there's a little bit of blue. It goes under the yellow one and under the green one. That's the total one. That's it. Anyway, and this is for different different plots, n equals 30, different beta equals 5. We can see that it's always there. It's always there. That dominance of this connected contribution at early times. In principle, before I go there, in principle, we should be able to see this also in the all-to-all SYK if we were able to go to high enough numerical simulations. But as I said, nobody does spectral form factor more than 40 something, I think. So that would be one thing to try in the future, if to see if we can confirm this in the all-to-all. But I think from everything that we know about the sparse model, it's very clear that it's also going to be a feature of the all-to-all. Okay, and then work in progress. So, oh yes, I'm going to be on time. Work in progress. Another way of diagnosing chaos is the out-of-time order correlator. And our goal here is to extract the Lyapunov exponent for the sparse model and see how it changes with the sparsity of the model. It's very difficult to extract numerically, but direct fitting. So these guys from Cobrin et al. That did some numerics on the autox, at large n, they had an improved numerical method that relies on these ansatz for f of t. F of t is this part of the octet. So having this ansatz, then you can cut through the plots. I will show you in a second. You can cut through the plots, and then you can numerically identify better what is lambda. But this implies that f of t obeys this symmetry. So the first thing that we have to check to do is if we calculate our autox in a sparse SYK, is really going to obey that symmetry. And if we just did it, right? I mean, we just did it, and it was not so obvious. It did not happen. The symmetry implies that the graphs are kind of ordered as you go larger in n, and it just did not happen. We had to do some additional averaging over hypergraphs, but eventually here they are. So now they are ordered as they should. So this is C of t, and these are the different k's. So different colors in this one are different k's. K 913 is the SYK. Is here. You can see k equal 4 is the next one. It's already pretty close, and while all the other k's. This is at fixed n equals 30 for 1,000 realizations. And then the way you determine the Lyapunov exponent is you choose, like, say, I think in their paper they choose something like q equals 0.3 or something. You choose an appropriate, which still yet to be determined which one is the appropriate, but you choose something, and then you can see where that curves cut that value and determine the Lyapunov exponent. So this is another one for different ends now. This is different ends with q equals 4, and well, they all satisfy that symmetry. So we have the autox. Now we just have to extract the Lyapunov exponent, and what I would like to see is how to determine how does that change with k and q. And so I'm wrapping up now. I'm almost out of time. So my whole theme is I want to explore different questions regarding the sparse SYK to determine from this quantum mechanical just point of view, like how good a model of holography it is, to put it in like a more solid basis. And then what I would really like to understand is the other side, right? The gravity dual of this story. But well, future directions. Oh yeah, I still have my next thing with the numerics and all that is there's this beautiful work by Heil and Shao that they look at how can you diagnose collisions behind the horizon, and it's this 6-point function that can tell you if two signals have collided behind the horizon or not. And they have very specific scaling of how this 6-point function should behave. So one would hope to be able to, in this little model that allows you for a lot of numerical control, also detect how signals have collided behind the horizon by reproducing the scaling of Heil and Shao. That's one thing that I'm trying to do with Shenlong Xu, who was one of the original authors in the Sparse SYK paper. More on hypergraphs, operator growth, and double scaling limit. There was a paper by Lenny not long ago saying that this is probably dual to de Sitter. So one could think about doing things in the sparse SYK and double scaling limit also. And that's it. That's all I have. Thank you.
Can you explain why it's not self-averaging or less self-averaging than dense SYK, or?
Well, I don't have a good intuition for why it is not self-averaging. I would say that if you think of it more in like the random pruning type of thing, you can see that it's probably like it's more intuitive to think that it's not going to be self-averaged. But honestly, I know that it's a result that it's not self-averaging, but I don't have a really great intuition about
You mean
it.
it's just something you see in the numerics?
It's something people see in the numerics, yeah.
So
I guess there must be some, wait, can I just finish? So I guess there must be some like canonical measure of
there must be something about the, yeah, there must be something when you like look at the partition function and something like that. I mean, now you have Brian is the one that worked in this kind of type of thing, and probably you can see it more clearly from that approach. But yeah.
Okay. Thanks.
So I'm totally confused about that statement. You said, yes, it's not self-averaged, but looking at the plateau region of a spectrum form factor, it looks like almost self-averaging.
Oh yeah, it's not self-averaging for all observables, right? Self-averaging, I understand it as you take one and it will give you the same as the average for if any observable anywhere, whatever. This one has, yeah, sure, the plateau and the early time is pretty smooth. That is okay.
Okay, for this quantity, it's self-averaging, right?
Yeah, yes. In this quantity, in that region at early times.
Okay, okay, that's the confusion I had. Okay, good.
Yeah, but it's not for any observable.
Okay, thanks.
I had a question about the traversable wormhole story.
Yeah.
So these plots that you showed where there are the oscillations going up and down, and then you also had the uncoupled SYK plot. And the uncoupled SYK decays to a value much smaller than even the, like when we sort of think of the signal having traversed the wormhole, gone from one side to the other, like if the signal was on the right and you looked at the left amplitude, it was still much larger than the decayed amplitude of the uncoupled.
I think that the uncoupled things decays to zero, right? Because
okay, so there's just some floor.
It's just
there's no story there.
You're not coupling the two things. So yes, yeah, the uncoupled thing just goes to zero because you don't have any coupling between these two things. That you could ask, which is something I still have in mind, and I don't understand very well, but whatever. You could ask, like, so this revival thing, why does it happen? You have this two SYKs and you couple, but the way you choose the couplings, they are not independent. They are random, but they are not independent. And that's what makes it possible, this revival thing. So you're choosing left and right, both randomly, but not independent, right? So what will happen if you choose random and independent couplings? So it's like your CFTs are different. I do not know that. I don't know what will happen, but that I think is an interesting question.